Welcome back, everybody. This is Mr. Strager. Today, we're going to be talking about Big Ideas, Lesson 2.6 on page 55. But before we can, we really should review a little bit of something from Unit 1. Now, I've talked many times about how Unit 1 and Unit 2 look very, very similar, and it's no different with this section, because today, we're going to be talking about absolute value once again. Now, last unit, I got a couple of people saying that absolute value was probably the toughest thing last unit, and I agree. Absolute value is not necessarily the easiest thing to solve. But at the very least, I do want to do a little bit of review about what it means and how to solve it. So when we go into this unit, we'll be feeling a little more comfortable. Let's say I told you that the absolute value of x equals 3. Well, what does this mean? Well, the absolute value of a number is a number's distance from 0. What this problem is saying here is the distance that x is from 0, distance that x is from 0 equals 3. And it's equals because we do have a physical equal sign there. The distance that x is from 0 equals 3. Well, it's kind of hard to conceptualize it when it's just in an equation, so let's try writing it on a number line. That'll give us a better idea of what we're looking at. If I have my 0 here, there's 1, there's 2, there's 3, there's -1, there's -2, there's -3. What numbers on this number line are exactly 3 away from 0? Take a second and try and ask yourself this question. The first one that I think should be the most obvious is 3. 3 is 3 units away from 0. It has a distance of 3. I'll say d, the distance, equals 3. If you got that one, that's sort of a very nice start, but the trickiest part is trying to find the other number that's 3 away from 0. And if you remember last unit particularly well, -3 is also going to be 3 away from 0. d equals 3, the distance. So when we had an equal sign, it was very simple because you would usually get 2 answers. A positive version and one that's a little bit closer to the negative side, or a very negative and one that's closer to the positive side. Of course, both of your answers could very well be a little bit different if you weren't trying to find the distance from 0. Overall, though, this is what we talked about last unit. To solve an absolute value problem, all we did was we would split up our problem into 2 versions of itself. Let's say, for instance, we had x plus 1 in our absolute value signs equals 5. We learned last unit that we can actually split this into 2 versions of the same problem. The first version of the problem, we write out the whole thing just the exact way it is. So we write our x plus 1 equals 5, and we would solve this. The second version of the problem, we had to change a little something. Does anybody remember what it is? If you said the right side becomes negative, then you are correct. So we would write out the problem exactly as is, except we would put a negative side in front of our whole right side. So we'd have x plus 1 equals -5. From here, we would solve like normal. To get x by itself in this first one, for instance, we would subtract 1 from both sides, giving us x equals 4. In this one, since we have x plus 1, we want to get rid of that plus 1, we would still subtract -1 from both sides, giving us x equals -6. This should be very familiar to us because, well, we did it a unit ago. But let's change things up slightly. What if instead I gave you the following problem? What if I told you that the absolute value of x is less than 3. In fact, let's make it less than or equal to, just to make things easier for us in the future. The absolute value of x is less than or equal to 3. Well, up here, we said this meant the distance that x is from 0 equals 3. So here, we would write it out as the distance that x is from 0 is, but it wouldn't equal 3. This time, it is less than or equal to 3. So the distance is less than or equal to 3. Well, again, this is very hard to conceptualize, so let's put it on a number line to make it a little bit easier for us. If I draw out my number line this time, again, going from -3 to +3, just to make sure there's enough room. There we go. We're looking for numbers that are less than or equal to 3 away from 0. So what numbers can we put on here? Well, if we're looking for a distance that could be equal to 3, that means that 3 could totally work. And if 3 is 3 away from 0, -3 is also 3 away from 0, so that should work. What else is less than or equal to 3 away from 0? Well, something that's less than 3 from 0 is 2. That's less than 3 away from 0. And since -2 is only 2 away from 0 in this direction, we would say that -2 is also less than 3 away from 0. The same applies for 1 and -1. Is 0 less than 3 away from 0? Yeah, it's not far away from 0 at all. It's exactly at 0. So even that would work as a point. When you start filling in some of the other points on here, such as maybe like 1/2 and -1/2, or 1.5 and -1.5, or you can keep going on and on and on, you'll eventually get a list of numbers that are all less than 3 away from 0, or exactly 3 away from 0. However, none of these points ever go further than -3 or +3. In other words, it's almost like we have a line of points that x could be that ends at certain other points. Are you seeing where I'm going with this? If not, let's try to represent just the ends of this with dots. Well, since we say that it could be equal to 3, the distance could be equal to 3, that means we would want to use a closed circle at 3, and a closed circle, at -3, and a closed circle at +3. And where do we say that x could be? Well, x could be anything that's in between them, right? So we would connect those up with a line, and hang on a second. This looks exactly like lesson 2.5 that we did last time. And if you notice that, you're correct. The solution to an absolute value inequality is a compound inequality. Let's try to write out this graph in terms of a compound inequality and see if it matches up. So try on your own to just look at this graph and write it out as a compound inequality. If you haven't paused the video at this point to try it out, I hope that we get the chance to, but if not, let's take a look. So the way we write out a compound inequality based off of a graph is by starting with our end in mind, starting with our endpoints. Our endpoints are -3 and +3, and we ask ourselves, is x outside of these points? So could x be all the way over here? Could x be all the way over here? Or is x in between? Well, since our line represents x, x is in between these 2 points. So we put x in between the -3 and the +3. Now all we need to do is put in the correct symbols. If we look at -3 over here, and we ask where's x in relation to that, well, our line x is bigger than -3. So we would face our crocodile this way. Could it equal -3? Yeah, x could equal -3. It's a closed circle. What about x and 3, which is bigger? Well, 3 is all the way to the right, and x is this line here. 3 is the bigger part. So our alligator is going to chomp down on the 3, and again, it's a closed circle, so we could say it's equal to. This is the compound inequality that's the exact same as this absolute value inequality. In other words, the way that we solve an absolute value inequality and the way that we solve a compound inequality are very, very similar. So, here's what I'd like us to take a look at. I'd like us to open up our notes again, and let's get down some of these definitions. To start off with, we've talked a lot about absolute value inequalities. An absolute value inequality is an equality with an absolute value in it. An inequality with an absolute value inside of it. We mathematicians are not very creative with our vocabulary. The other vocabulary word that we're going to be seeing later on in today's lesson is absolute deviation. This is a little bit more complicated, so if you don't get it the first time, don't worry. But the absolute deviation of a number x from a given value is the absolute value of the difference of x and the given value. So when we talk about the absolute deviation, we'll talk about it in a second. This is going to be a little bit different than our normal absolute value inequalities. Let's go down to the bottom of our notes and actually see if we can take a look at these absolute value inequalities. Down here we have a lot of algebraic jargon, but the key thing to pick out is this. To solve an absolute value inequality where we have a less than symbol or a less than or equal to symbol, it's the same as having an and compound inequality. On the other hand, if you end up finding that your absolute value inequality has the absolute value greater than the right side, it's going to be an or compound inequality. So for these two symbols, it's or. Let's try out some of these things, and let's see how we can actually go through and solve them. So I'm going to write this down in this section here. I'd like you to write out on one side the word and on the other side I'd like you to write out the word or. So when we have an absolute value inequality that looks a little something like, for instance, x plus 7 on absolute values is less than or equal to 2, we would solve it in much the same way that we would solve a regular absolute value problem, with a little bit of a twist. So just like before, we want to split as soon as we have our absolute value all by itself. It has to be all by itself before you can split, though. Since there's nothing else on this side but the absolute value, we can split. So our first version will look exactly the same as this. We'd have x plus 7 is less than or equal to 2. And we would solve this like normal. The difference is in addition to making our right side negative, we also want to flip our inequality symbol. Just like when we multiply or divide by a negative, we're really multiplying the entire right side by a negative number. So we have to flip our inequality symbol. Instead of having x plus 7, all in absolute value, is less than or equal to 2, it's going to be x plus 7 is greater than or equal to 2. To negative 2. We flipped our symbol and we made the right side negative to do that. From here, we just need to solve like normal. So we would subtract 7 from both sides of this left version, leaving us just x is less than or equal to negative 5. On this right version, if I subtract 7 from both sides, these cancel out, and negative 2 minus 7 gives us negative 9. The last thing is, since it is technically an and compound inequality, we want to combine these two into one statement. To do that, we list off our endpoints in order from least to greatest. Negative 9 is the least, negative 5 is the greatest. Because it's and, our x is going to be in between, and we face our signs the same way they're facing in these two. Here, our sign is gobbling up the negative 5, so negative 5 is still going to be gobbled up between the x. Here, our x is being gobbled up with regards to our negative 9, so it's still going to be gobbling up our x. That's our final answer. You do have to be very, very careful about making sure that you can only split once everything is entirely by itself, once the absolute value is all alone. Let's try another problem, but this time we're going to make it an OR inequality. So I'm going to bring out a different piece of paper for this one because I'm also going to make it just a little bit trickier. All right, let's say we have the following problem. The problem that we're going to look at now for the OR is the absolute value of c minus 1 minus 3 is greater than or equal to 2. This is a little bit different. Can we split right off the bat? Unfortunately, we can't. We can only split when the absolute value is all by itself, and it's clearly not by itself in this case. We have this minus 3 attached. Well, that's no worry for us, though, because we know that we can get rid of this minus 3. How do we get rid of minus 3 from this left side? By adding 3 to both sides. This will give us the absolute value of c minus 1 is greater than or equal to 5. Now that c minus 1 in absolute value is all by itself, we can now split. The first version will be just written as is without the absolute value symbols, so c minus 1 is greater than or equal to 5. The second version, we want to flip our symbol and make the right side negative. So c minus 1, instead of being greater than or equal to, it's going to be less than or equal to, and instead of 5, we will have negative 5. Try to see if from here you can solve the rest. If you just want to watch along with the video, here's how we do it. We want to get c by itself, so to get rid of this minus 1, we would do the opposite by adding 1 to both sides. So c is greater than or equal to 6. On this one, it's the same deal. We still want to get rid of minus 1, so we would add 1 to both sides. We would end up with c is less than or equal to negative 4. Of course, because it's an OR inequality, we would write the word OR in between. But let's say you didn't know that it was an OR inequality. Is it possible for a number to both be bigger than or equal to 6 and less than or equal to negative 4? Well, no, a number can't be positive and negative at the same time, so it has to only work in an OR context. Otherwise, it would have no possible solutions. There is one more problem type that we would see in day 1 of this lesson that I want to talk about real quick. And that is, in the Big Ideas homework, you might have seen a problem that looks something like this. Let's say we had a problem, or we had the absolute value of 8x minus 11 is less than or equal to negative 2. Before you even solve a problem like this, we have to ask ourselves, hang on a second, do we remember what we did last unit when we talked about absolute values? Absolute values can never be negative. This inequality is telling us that our absolute value has to be even less than or equal to negative 2. Is it possible for an absolute value to be less than negative 2 or equal to negative 2? In both cases, it just can't happen. The absolute value makes whatever's inside of it positive, so we would end up with a positive number over here. Because there is no x that would make this true, we say it has no solutions. Let's change things around just slightly, though. Let's say we had the absolute value of 8x minus 11 is, let's go with greater than or equal to negative 2. Well, again, we got to ask ourselves, is it possible for it to be equal to negative 2? No, it will never be negative 2. But will it be greater than negative 2? Well, yes, it has to be bigger than negative 2. Our absolute value will become just a positive number. So it's always going to be bigger than negative 2. Meaning, we would end up with all solutions for this particular problem. At this point in time, you have enough knowledge to take on day 1 of Big Ideas. If you would like to continue watching, we'll be talking about day 2 in just a moment. So try out day 1 of Big Ideas, and stick around for day 2 of the notes. All right, so if you keep watching up until this point, you will know that this is day 2 of the 2.6 notes. So in day 2, we started off by talking a little bit about one specific problem type. We talked a little bit about the homework and how there was a negative answer, sort of like how we discussed at the very end of our last video. But there's another problem type that I want us to take a look at so we know what to do. So that problem type is this. Let's say we have the following. We have the absolute value of x divided by negative 2 minus 4 is less than 0. What do we know about this problem right off the bat? We know it's going to be an and inequality because our less than symbol is here. Anytime our absolute value is less than the right side, it's an and. So we're going to be ending up with 2 endpoints, and our x is going to be in between those 2 endpoints. Let's put that to the test. So what do we need to do first? Can we split? If you said no, you're correct. We cannot yet split this problem because we've got this minus 4 that's still here. You can only split when all you have left is your absolute value. So let's add 4 to both sides. When we do, these ones will cancel out. 0 plus 4 is 4. And since we didn't multiply or divide by a negative, then everything is going to stay the exact same way it was. Now can we split? Yes, now we can, because all we have left over is our absolute value on the left. So we would take our split. The left version is going to look exactly the same as this. So we write it out exactly the same. X over negative 2 is less than 4. On the right version, what do we need to change? We're going to make our 4 negative and flip our symbol. So we have x over negative 2 is greater than negative 4. All right. Now we're getting somewhere. At this point, this is where we have a little bit of a problem. Because what happens? First of all, what do I need to do to get rid of dividing by negative 2? we have to multiply by -2, because multiplication is the opposite of division. But what do I need to do anytime I multiply or divide by a negative? We have to flip our symbol. In other words, we go from a less than to a greater than. 4 times -2 is -8, and x is all by itself. So x is bigger than or greater than -8. Here, we do the same thing. We're multiplying by a negative, so even though we just flipped it, we got to flip our symbol yet again. We're flipping it back to the less than symbol because we multiplied by a negative. We end up with x is less than 8. Does this make sense as an AND inequality? Well, are there numbers that are bigger than -8 and less than +8? Yeah, 0 works, 1, 2, 3, 4, 5, 6, 7, -1, all of those numbers work. So this is still correct. All we need to do now is put these together. To put together our AND inequality, we're going to start off by listing our endpoints, starting from the lowest, ending with the highest. Since it's an AND inequality, again, because we have a less than symbol after our absolute value, our x is going to be in between -8 and 8. So our symbols are also going to always follow the biggest number. X is less than 8, so x is less than 8. X is greater than -8, so -8 is less than x. Very nice. Now, today we're going to be talking a little bit about absolute deviation. And absolute deviation is interesting to say the least. Last time, we talked about how the absolute deviation of a number, x, from a given value, is the absolute value of the difference of x and the given value. Wow, that's a lot of words. Well, what does this mean? It means the following. Our absolute deviation, is equal to the absolute value of x minus our given. In other words, this is basically saying, hey, this is how far away we can be from a number we're given, and x, when we solve for it, will give us how far away that is. That's sort of abstract though, so let's try one together. Let's say I told you that my absolute deviation is equal to 3. And I'm telling you, well, let's actually use some units here. Let's say my absolute deviation is $3, meaning I can spend $3 more or $3 less than what is originally given. Let's say that my parents give me $20. My question is, between what prices would I be able to purchase with this money? Well, our formula says our absolute deviation, which is 3, is equal to the absolute value of x minus our given. What this means in sentence form is, hey, the amount I spend minus 20 will be, let me actually rewrite this, I'm sorry, y'all. Let's say I want to spend less than $3 greater or less. So I apologize, we should have actually technically had this symbol here. What this means is, I can spend anywhere from $23 to $17. Well, how do I get 23 and 17? That's what's $3 away from 20. 23 and 17. Mathematically, it solves like this. We would do our split, and just for simplicity's sake, I'm going to flip everything, just because we've always dealt with our absolute value on the left. If you want to keep things the way they are, that's fine. You can keep them the way they are. But I'm going to flip everything just to make it easier to see that, hey, this is the side that we're going to be changing to be negative, which, by the way, we will be doing in the next part here. X minus 20 is greater than or equal to negative 3. What this means is, again, we split and we flipped our symbol and made this negative. When we solve by adding 20 to both sides, this will give us the amount of money that we can spend. So we can spend less than or equal to $23. Or, when we add 20 to both sides, we can spend greater than or equal to $17. So in other words, the amount of money we can spend, X, is in between $17 and $23. But since I kind of fiddled with that explanation a little bit, let's try one more together. For those of you who want to follow along, this is going to be number 10 in our student journal. At a certain company, the average starting salary, S, for a new worker is $2,500. That's the given. The actual salary has an absolute deviation of at most $1,800. And our goal is to write and solve an inequality to find the range of starting salaries. So it is a word problem, but the good news is when we have an absolute deviation word problem, all we need to do is plug in what we know. Our formula, remember, is that the x minus the given, all in absolute value symbols, will have some inequality here compared to the absolute deviation. Here, it's going to equal whatever our absolute deviation is. In these types of problems, keep in mind that this equal sign is probably going to change into a less than or a greater than or less than or equal to or greater than or equal to based on the problem. Based on the problem, we can tell what this symbol is supposed to be. So, in this problem, let's start thinking. Our average starting salary is S. That's how much we're starting at. And from that, we can assumedly add or subtract a certain amount of money. So S is our variable. Well, it's our given. The typical salary is our given, $2,500, or $25,000, I should say. So what we end up with is the absolute value of S minus 2,500, or 25,000. If you don't believe me, it tells us that our absolute deviation is at most $1,800. Now's where we got to think about what symbol to put in between. The words it gave us were that the absolute deviation is at most $1,800. What does that mean in terms of the problem? Can our salary be $1 million? No, because if we're starting at $2,500 and our absolute deviation is at most $1,800, it means it's not going to be much higher or much lower than $25,000. What this means is we're looking for a number that's in between whatever 25,000 plus 1,800 is and 25,000 minus 1,800 is. It's an and inequality. Anytime your absolute deviation gives you a range that you're supposed to be in between, or the problem is looking for some salaries, for instance, that you're trying to find the range in between, it's an and inequality. So we want to use the symbol that correlates to that. You could have also figured it out because the words at most means less than or equal to. If I tell you can have at most 2 pieces of cake, that means your x is less than or equal to 2. Here it's the same thing. The absolute deviation is at most 1,800. So this is less than or equal to 1,800. Enough of that though. At this point we have enough to solve. I want you to pause the video and try and solve this if you can. Hopefully we paused the video and got to try it out. If you didn't, here's how it's going to work. We do our split like normal. S minus 25,000 is less than or equal to 1,800 because that's the same as up here. When we write our other side, remember there are two things that change. The first is our symbol flips. So it's going to be greater than or equal to now. And our right side becomes negative. Negative 1,800. If we're having trouble remembering right or left or figuring out when to make it negative, it's the side that the absolute value is not on. I just like to keep it on the right side for consistency's sake. From here, all you need to do is solve for s. So we would add 25,000 to both sides, giving us s is less than or equal to $26,800. Over here, we would do the same thing. We would add 25,000, giving us s is greater than or equal to negative 1,800 plus 25,000. That's going to give us 23,200. So s is less than 26,800 and more than 23,200. We always want to write it out as one simple inequality instead of two connected by an and. So our lower number is 23,200, and this is dollars. Our higher number is 26,000. I'm going to write this on a separate sheet of paper. I apologize, y'all. Our lower number is $23,200. Our highest number is $26,800. And our S, our salary, is somewhere in between that two. So it's in between. Of course, our symbols always need to follow our rules of alligators. The alligators are always going to eat the things that are biggest. 26,800 is bigger than S, so it follows there. And S is bigger than our minimum of 23,200. This is very useful for finding the maximum and minimum of a situation. But we'll be talking about that a little bit later in the course, and if I see you in statistics, we'll be talking about it then. So that's what the absolute deviation is. There's one more problem type that you might see. Obviously, this word problem was, very wordy. That's why it's a word problem. But let's see if we can apply the absolute deviation to a problem that looks a little bit more like this. Let's say we had the problem. A number is 9 more units, I mixed this up. I apologize, everybody. A number is more than 9 units away from 3. A number is more than 9 units away from 3. Well, some of us have already thought of what the answers could possibly be, but let's keep this in mind. In order to write this out, we want to write an absolute value that represents the situation. It might help us to remember the absolute deviation formula, which says that our absolute deviation is equal to our starting number, or our x, if we don't know our starting, minus whatever we're given. In this case, well, x is a number, right? We know that a number always means x. So, x. It's more than 9 units away from 3. If we used our absolute deviation formula, we know that, hey, we could add 9 to 3, or we could subtract 9 from 3. But either way, 3 is our starting place. It's our given. To show this, we're going to write out x minus 3 in our absolute value brackets. And since this whole thing is more than 9 units away, we use a greater than symbol and our 9. It's sort of hard to conceptualize sometimes, but the idea is your x should always go with wherever your starting point is, or your given. In this case, our starting point is 3, so we write x minus our starting point. From here, all we need to do is solve. So take a minute, try to solve it, and we'll come back. Hopefully we pause the video and we're able to go ahead and solve it. We split this problem into two versions. X minus 3 is greater than 9, and we do a version where we flip the symbol, so x minus 3 is less than negative 9. To solve, there's only one step for these problems, adding 3 to both sides. We end up with x is greater than 12. We also have, by adding 3 to both sides here, x is less than negative 6. You can tell that it's an OR inequality because we have our absolute value greater than another number. So if you use that in mind, you can just write the word OR right then and there. But if you can't remember, think. Is there a number x that's both bigger than 12 and less than negative 6? No, because this would have to be a positive number and this would have to be a negative number. So clearly there's no number that works for both. It's an OR inequality. So this is our answer. All right, everybody. Hopefully we had a good chance to try some of these problems out. As a reminder, use the absolute deviation formula to help you with word problems, even when you're just trying to write out an actual inequality. With that being said, have a spectacular rest of your day, and I'll see you next time.